if there are questions. If there are questions, please just interrupt me and let me know, okay? If you would like some background material on what I'm going to talk about, I spent some time writing a review. It's given at the bottom. You can find the archive number. It's a review in the annual review of astronomy and astrophysics. So that contains background that you might find helpful. Okay, so let me start from the beginning. Sorry, let me see. So the evidence for dark matter, I don't think I need to belabor. I hope this in this audience is fairly familiar. Essentially, we know dark matter is there through its gravitational effects, and its gravitational effects show up in many ways. One of the oldest ways is by looking at rotation curves. This is what I call dynamical measurements. More recently, we can look at the gravitational effects of dark matter through its effects on photons. So a phenomenon we call gravitational lensing. And also in how dark matter affects the growth of perturbations, which manifests itself perhaps indirectly through the anisotropy we see in the microwave background. And all these different methods point towards the existence of dark matter. So at this point, the evidence is so rich, I think the existence of dark matter is not in doubt. There have been discussions in the past whether it's possible that dark matter does not exist, but instead is that we have got our idea about gravity on large scales wrong. By now, I think that option is more or less close. We know we have actually ways to even test those ideas. One of which actually is what the middle picture about lensing, that's what that is about. But I'm not going to go into detail of that unless there are questions. So I'm going to take that for granted, and I'm going to move on and say something about actually our ignorance about dark matter. No, so we are fairly confident dark matter exists. However, we are very ignorant about its basic properties. For example, if dark matter were some kind of particle, what is the mass of that particle? And this spectrum down here in electron volts illustrate essentially how ignorant we are. You know, basically this whole many orders of magnitude in mass, they are all allowed by data essentially. On the lighter side, the most common option that you might have heard about is axion. Axion in this talk could be the QCD axion, but it can also be some kind of axion-like particle. On the heavier options, there is a WIM, weakly interacting massive particle. On the even more heavy option, it could be objects that are really heavy, meaning they are as heavy as stars or black holes, tens of solar mass. So all those options are, at some level, they are all allowed. So it kind of this really illustrate how ignorant we are about some fundamental properties of the dark matter particle. However, in this spectrum, there is actually one interesting scale. And let me tell you about that interesting scale. And it comes from asking the following question. First of all, let's make the following observation, right? So from dynamical measurements, looking at motion of stars in the solar neighborhood, that motion actually tells us the local dark matter mass density, and is of this order of magnitude is about 0.3 GeV per centimeter cube. So this number we are fairly confident about. This is the mass density. Now we can ask the following question. If I take the dark matter particle mass, for any given particle mass, this mass density would imply a certain number density. From that number density, we can infer the interparticle separation. And we can ask the question, at what mass is the interparticle separation less than the Broglie wavelength? Right? So we are basically asking, if I imagine I take the particle mass and I make it smaller and smaller, what is going to happen? Well, to match the observed total mass density, the number density has to increase if you decrease the particle mass, which means the particle separation becomes smaller and smaller. On the other hand, the de Broglie wavelength goes like 1 over m. In fact, it's 1 over mb, right? In this talk, h bar is set to 1. This is actually h bar over mb. B is just typical velocity in the Milky Way. As you make the mass smaller and smaller to the left end of this spectrum, the de Broglie wavelength becomes big. The interparticle separation becomes small. And so there has to be a point where basically this inequality is established. And you can ask, at what mass scale is that established? And it turns out to be this number, if you actually work it out, is around 30 electron volts. There is one number that I have to input here in addition to the 0.3 GeV per centimeter cube. You have to input the velocity, the typical velocity of that matter particle. In the Milky Way, we actually know that fairly well. The Milky Way velocity dispersion is about 250 kilometers per second. So that's where this 30 electron volt comes from. I actually assume V is around 250 kilometers per second, given this observed total mass density. So if you have a mass that's lighter than 30 electron volts, this is what I'm going to call the wave regime. So we are in a regime where if I draw a sphere with a radius that's equal to the de Broglie wavelength, that sphere would contain multiple particles. And if I go to very, very light masses, that sphere would contain many, many particles, right? So the de Broglie volume contains many particles, multiple occupancy. That can only happen, by the way, if these particles were bosonic. If we were fermionic, you cannot have high occupancy, as you know. You cannot even have multiple occupancy in a single state. But for bosons, that's not a problem. So we are in what I would call the wave regime. And in this talk, when I say the wave regime, perhaps the most helpful way to think about it is to think about photons. No? For photons, we know if you give me a state of photons with many, many photons, for most generic states, that state of photons can be very well described by just classical electromagnetic waves. This is what I mean by the wave regime. So just like for E&M, a state with many, many photons is often very well described by a set of waves, classical electromagnetic waves. Here, we are talking about the same thing. Dark matter waves, classical dark matter waves is a good description when this inequality is satisfied, when the mass is light enough so that the interparticle separation is less than the de Broglie wavelength. Now, to give you a sense of scale, I give a few representative numbers. When you are close to 30 electron volts, the de Broglie wavelength is small, right? It's less than a centimeter. But if you go to a scale that is 10 to the minus 6 electron volts, 10 to the minus 6, I picked that number because it is the target mass of some axion detection experiment. For example, ADMX, which is a microwave cavity experiment. The de Broglie wavelength is about 1/10 of a kilometer, which is actually sizable. If you think about the scale of these experiments, the experimental device for detecting axions is actually smaller than this scale. This scale is in fact relevant if you want to interpret these axion experiments correctly, which is part of what I'm going to talk about. If you make the mass ultra small, 10 to the minus 22 electron volts, this kind of mass is often called fuzzy dark matter. And the de Broglie wavelength, the corresponding de Broglie wavelength will be astronomical, right? 100 parsec. Again, for velocity, which is around 200 kilometers per second. So in this talk, when I say wave dark matter, it refers to any mass less than about 30 electron volts. The term that you might have heard about, fuzzy dark matter, I'm going to reserve it for the extreme ultralight limit, around, let's say, 10 to the minus 20 to 10 to the minus 22 electron volts, where the Broglie wavelength is astronomical, okay? And there have been a lot of work already thinking about WIMPs, thinking about dark matter as basically particle dark matter. There have been correspondingly less work, although recently has become more popular to think about this, but correspondingly less work to think about dark matter in the wave regime. And that's what I want to talk about today, to explain some of the interesting phenomenological implications of wave dark matter. Okay, and here is an outline of the talk. I want to spend maybe the next 10 minutes talking about particle physics motivations. You know, what would be a good, well-motivated candidate from a particle physics point of view for such a light particle, a light bosonic particle. And by the way, in this talk, I will mostly focus on a spin zero. So it's a scalar field, basically, a spin zero particle. So I will focus on that and talk about some motivations from particle physics point of view. And then most of the talk, maybe after that, maybe for the next maybe half an hour, I'll talk about the basic wave dynamics and phenomenology. And in particular, I want to kind of draw out some of the implications for astrophysical observations, which are mostly relevant if your dark matter mass is really ultralight. Again, by ultralight, I mean around 10 to the minus 22 to 10 to the minus 20 electron volts. And I hope I will end with some discussions of the experimental implication, meaning implication for axion detection experiment. For those experiments, typically the target mass is not ultralight, maybe around 10 to the minus 6, although there's a pretty big range. I will talk about that as well. Let me I think it works best, especially online, so that I can have some feedback from you.
Sorry, may I ask you, how do we know the typical velocity of the dark matter in our galaxy?
Very good. So it works something like this. Dark matter, of course, we cannot see them, right? So we cannot see the dark matter particles. So it's a very good question. How do we even know how fast they move? What we do know, we can actually directly observe is the motion of the stars, right? We can see how the stars move around the Milky Way. And we know the velocity dispersion is roughly a Maxwellian velocity dispersion. And the velocity dispersion is around 250 kilometers per second. Then you invoke the basically the equivalence principle. What the equivalence principle tells us is the following, right? Under gravity, all objects fall at the same rate, regardless of its mass. Therefore, whether your particle is a star or a dark matter particle that is much lighter than a star does not affect the rate at which it falls. So under the total gravitational field of the Milky Way, and after the Milky Way has established some kind of equilibrium, basically variable equilibrium, all particles, regardless of its mass, should have the same velocity dispersion. So that's how we know. Does that make sense?
Yeah, that makes sense. Thank you.
Thanks for asking. That's a good question. Are there other questions? Very good. Let me start with this first line. If I tell you I have a particle that is a scalar, a spin zero particle, and is very light, a very natural guess, it would be some kind of pseudo Nambu-Goldstone boson. It would be an exact Nambu-Goldstone boson if that particle were actually have zero mass, right? This is what this picture is supposed to remind us, right? If you have a Mexican head potential, like what this picture illustrates, the vacuum, which is basically the set of minima for this potential, forms this circle, in this valley. And if this Mexican head potential is exactly spherically symmetric, this set of vacua down here, they are all going to be equal in potential. And the excitations around this circle, which I illustrate with phi here, it would be the Goldstone boson. And that would be massless. And I added the word pseudo here. This is a common practice. A pseudo Nebu-Goldstone boson means this is a particle that at a perturbative level is indeed a massless Goldstone boson, but quantum mechanical effects, in particular non-perturbative effects, often generate a tiny mass for the particle. One way to visualize this is instantons, for example, can basically tilt this potential just slightly by a small amount. And by tilting this potential by a small amount, there would be, instead of a whole circle of minima, there would be one preferred minimum around which the excitations, this excitation basically in the angular direction will now acquire mass. And these non-perturbative effects is in general exponentially suppressed. That's why the mass is small. And in case that's not familiar, let me use the analog that you might be familiar with in quantum mechanics. You know, in quantum mechanics, one non-perturbative effect that we often talk about is tunneling. Tunneling is described by a process whose probability is exponentially suppressed, right? And these instanton effects that generate a potential for the Goldstone boson is similar. It's also exponentially suppressed by some kind of instanton action. And assuming the instanton action is like 10 or 100, that is enough suppression to give you a small mass. So that's basically the picture one has in mind. The most well-known example is the QCD axion, which was invented by Pesce and Quinn to solve not the dark matter problem, but the strong CP problem, namely why the neutron dipole moment is so small. In fact, it's consistent with zero. And the cosmological implications was later spelled out by a large number of people. More generally, there are a lot of particles that are predicted from string theory, motivated by string theory, that are axion-like. They are not the QCD axion, but they behave in a way, in a sense, quite similarly. They are often called axion-like particles. Essentially, they arise in the following way. String theory, as you know, requires having extra dimensions. And when you have gauge fields or higher form fields in extra dimensions, if you do dimensional reduction of the Kaluza-Klein modes, the zero modes of these fields behave like an axion particle, basically. And in fact, in string theory, there are lots of such particles. And this is something that has been discussed quite a bit in the literature. I gave you some reference here. In any case, either the QCD axion or some sort of axion-like particle seems like a good candidate for a very light scalar or spin zero particle. There is an additional motivation for thinking about an ultralight scalar particle. Let me tell you about that motivation. And it's basically this footnote that I intended to discuss with you. And here the mass can be really ultralight, although as you will see in a moment, the mass range is still very wide. It is not confined to precisely this value. So the motivation things come from thinking about relic abundance from the Big Bang. So let me start from the beginning, right? Suppose I have this Goldstone, I call phi here. If this Goldstone were exactly massless, then all you should have is this kinetic term, right? Plus perhaps derivative interactions, which I'm going to ignore. But because of instanton effects or non-perturbative effects, generally you generate some kind of potential. The potential has to be periodic because essentially this Goldstone is, phi is like an angular field, is periodic. But this potential, if you expand out, Taylor expand in powers of phi, you can see there is an m squared phi squared term, meaning this potential tells you your your axion actually has a mass. The scale here is set by basically two things. One, which I call F here, in the literature is called the axion decay constant. This F is essentially define the energy scale associated with the angular direction, right? The axion is a spin zero scalar, so it has in 4 dimensions is the dimension of mass. And for it to represent an angle, you have to take this phi divided by another mass scale or energy scale. And that scale turns out is often called the axion decay constant. If you want, F basically define the energy scale such that if you go around once, you basically get this scale. It's a periodicity scale going around the angular direction. That's what F is. The other scale is this lambda. This lambda is the mass scale that actually set the size of the potential. And as I emphasized before, this lambda should be very small. It's exponentially suppressed. And the reason why it's exponentially suppressed is very analogous to the way tunneling is exponentially suppressed in quantum mechanics. This is basically the quantum field theory analog of that. From instanton or non-perturbable effects, it generates something small here. And if you Taylor expand this cosine out to phi squared, you can read off the mass. And the mass would be of this order. M would be the mass, what you will interpret as the mass of the axion, right? Okay, so let me tell you the argument based on what is called the misalignment mechanism. It is a way to infer the radical abundance from the Big Bang. And the story goes something like this. It's actually fairly simple to explain. So this potential, let me sketch out for you. It looks something like this. V over one period, it looks something like this. But remember, V is actually periodic, so it keeps going, but I'm drawing just one period. And let's imagine this phi in the early universe takes some value. That value, we have no idea what that value is. A very natural guess without fine-tuning is that whatever this value is, phi over F should be order 1. It's neither fine-tuned to be too small or too close to pi or 2 pi, but something like order 1. Seems like a natural expectation, but it is an assumption I want to emphasize. So suppose the initial field value is of the order F, and this is in the literature, people would say the initial misalignment angle is order 1. The misalignment angle means the initial phi over F is order 1. They call it misalignment, meaning it's not at 0, it's offset from 0, but it's order 1. Now, if you go back to the early universe, the expansion rate of the universe is so fast. There's a lot of Hubble friction. This scalar field would just get stuck here. It was not going to move, even though the potential would prefer to pull the scalar field down. This goes on until the expansion rate slows down enough to match the mass scale, which is this M here. At that point, Hubble friction now becomes less effective, and the potential now actually exert the pull and pull the scalar field down. The scalar field is going to oscillate around the bottom of the potential. And the expansion of the universe will go on, taking energy out of this oscillation. And so the oscillation amplitude is going to get smaller and smaller. Okay. Now, this oscillation of the scalar field around the minimum is precisely what we call dark matter. So this, if you want, represent a collection of dark matter particles. The fact that the oscillation amplitude gets smaller and smaller because of the expansion of the universe, that's precisely the phenomenon in which under expansion of the universe, the dark matter particle density redshifts like 1 over volume. So it matches that expectation, which is partly why we like to interpret this as basically a collection of particles oscillating around the minimum. And in fact, the oscillation amplitude gets so small that you can actually just replace this whole potential and approximate it as m squared phi squared, because you are now very close to the minimum. You can forget about this whole cosine structure. M squared phi squared is a very good approximation. And then it really behaves exactly like a cold dark matter. And if you follow this story, it is possible to predict what is the abundance today. And I'm skipping that part of the calculation. If you actually work out what is omega matter, which is basically the fraction of matter, dark matter produced this way as a fraction of the critical density, is around what you need to match observation. Observation is around 0.3 or something like that. If the axion decay constant is somewhat large, 10 to the 17 GeV, so this scale is somewhere between Guth scale and Planck scale. And this scale seems to be fairly common in constructions of string theory. And if the mass is ultralight, 10 to the minus 22 electron volt. But I want to emphasize, if you look at this formula, the regular abundance clearly is much more sensitive to your choice on F than the choice on M. And because the axion decay constant F is very uncertain, it could easily change. And even a small change, as you can see in this formula, because this is square and the M dependence goes like 1/2, even changing F a little bit, M is going to change a lot. And so one should keep in mind, while this argument seems to suggest a rather light dark matter mass seems to be a kind of a good target, but there is really a very large possible range. And we should always keep that in mind. We really do not know. But nonetheless, I take this as an interesting argument for why we might want to think about dark matter particle mass that is very light. Okay, this is from a radical abundance argument. By the way, for those of you who are familiar with QCD axion, the misalignment mechanism for the QCD axion is basically the same as what I told you, with one modification. In the case of the QCD axion, the potential is actually temperature dependent. It depends on whether you are after the QCD phase transition or before the QCD phase transition. So the final answer is going to be a bit different from this, but the story of misalignment mechanism is more or less the same. And in the case of the QCD axion, in fact, it was discussed in these early papers by these authors. Okay, so this is what I have to say about particle physics motivations. Any questions? Okay, very good. So I'm going to now turn to talk about the basic dynamics.
Sorry,
yes, please.
Just a comment that in the case of QCD axion, also the F is related to M. So you have like a small window for...
Yes, exactly. So for the case of, thanks for pointing out, for the QCD axion, essentially this lambda would be close to the lambda QCD. It will be close to the pion mass. So once you choose that lambda, then M and F has to be related in this way for QCD axion. And you can plug in what I assume here. So if you plug in F of this value and M of this value, the corresponding lambda is much smaller than the QCD axion, than lambda QCD, than the pion mass. And so this choice of values for F and M is emphatically not the QCD axion. It's more like one of these string theory axions. Yeah. Very good. Are there other questions? Okay, so I see that I'm already behind. I have about maybe 25 minutes. So let me tell you about the basic dynamics, okay? I already told you, if you follow the story I said before, essentially after redshifting for a while, the potential is well approximated by m squared phi squared. You're oscillating around the minimum. And so the dynamics of this axion is very simple. It's just basically the good old Klein-Gordon equation. Yeah. And in particular, for the purpose of cosmology, we are interested in the axion being in the non-relativistic regime. For example, the dark matter particle inside the Milky Way, they do not move very fast. They move at 200 kilometers per second, much less than the speed of light. And so for many applications, it's useful to take the non-relativistic limit, and it's a fairly standard thing to do the following. You take the axion field, which is a real scalar. You introduce a complex scalar, which I call psi here. You factor out the main time dependence, which is e to the IMT or minus IMT. That time dependence is designed to basically cancel this m square, right? If you take this and plug in. And then, of course, you add complex conjugate to make this a real scalar. And in the non-relativistic limit, the crucial assumption is that psi, this complex scalar, has slow time dependence. Slow compared to what? Slow compared to the scale set by m, basically. That's the assumption. So when you take this and plug into Klein-Gordon equation, if you encounter one time derivative on the complex scalar, the idea is to keep it. But if you encounter double time derivative, you can just throw it away because the time dependent of psi is slow. And again, slow compared to basically the scale set by m. So if you do all these, it's a very standard textbook thing. You would write down actually an equation that resembles the Schrödinger equation. In fact, that's why psi is often called the wave function. And the only symbol in this equation that I have not introduced is here is the gravitational potential, because here we are interested in basically only one interaction, which is the gravitational interaction. And to include that, you should include the gravitational potential here for this wave function. And this gravitational potential should be sourced by the density. And if you are in an environment that dominated by dark matter, then the density would be nothing other than the mass of the particle times the wave function square. Meaning you can really interpret the wave function square as representing the number density of the axion particle. Okay, so that act as a source for gravitational potential. This is just Newtonian gravity. And given that potential, you can plug into here and solve the Schrödinger equation. So these two equations form a closed set of equations that you can go ahead and solve and try to predict what is going to happen. What are the interesting phenomenology? The only thing missing in these equations is in cosmology, you might want to include the expansion of the universe, but that is actually fairly easy to include. The basic physics are contained in these two equations. Any questions about that? Okay, so I'm going to skip a number of comments. Do I want to go through? Let me at least mention this point of view. There is some sense in which this system, this Schrödinger-Poisson system, can be also thought of as a fluid. You might have actually seen that discussed. In fact, it's often discussed this way when people discuss superfluid. The wave function consists of an amplitude and a phase. The amplitude is really what tells you what the particle number density is. So again, the mass density is the mass of the particle times number density square. And so square root of rho over m, that describes the amplitude of the wave function. It's a complex number, so there has to be a phase. The phase is what I call theta. And it turns out from the Schrödinger equation, which is a complex equation, you can actually write down an equation for the amplitude and an equation for the phase. And they look like these two equations. The equation for the amplitude, rho dot, looks like mass conservation for a fluid, as long as you interpret the velocity of the fluid as the gradient of the phase divided by m, okay? Again, h bar is set to 1. And then if you work out an equation for the phase, which is, the gradient of the phase time derivative thereof, this equation looks like Euler equation for a fluid. The left-hand side is very standard in Euler equation. Essentially, it tells you the acceleration of a fluid element. The right-hand side represents basically the forces that actually give rise to the acceleration. The first term is not a surprise. It's the gradient of the gravitational potential. It's a gravitational force. The second term is often misleadingly called quantum pressure. It's actually not quite a correct term, but I'll call it anyway because it's a very common terminology to call it quantum pressure. And it arises precisely because because you have wave nature. You are really talking about something that comes from the Schrödinger equation. Okay, writing this way is helpful for some purposes. For example, if you look at these two equations, suppose I take the limit m becomes very big, mass is very big. In that limit, you can ignore the quantum pressure term. Then the Euler equation looks like just an equation you will write down for any cold dark matter, because the acceleration is just dictated by the gradient of the gravitational potential. There's no fluid pressure or anything like that. But when this term is non-negligible, it's basically telling you wave effects are important. Okay, so the particle limit, if you want, the WIMP limit is the limit when m is large. This term is negligible. In this talk, we are precisely interested in the regime where this term is not negligible because m is actually not that big, it's small, okay? So these equations are helpful from that point of view. Okay, I should say there's a whole discussion one could have about the meaning of the wave function. Let me skip it. If you're interested, I can talk to you. I'll be happy to talk to you about it. You can consult actually Feynman Lectures Volume 3, which has a nice discussion about this. And there is a last set of papers talking about scalar field as possible dark matter. I should mention that. Some of these are very old work, actually. So when I talk about wave dark matter, the first thing I want to impress upon you is because you have waves, it's inevitable you have wave interference. So this is a picture taken from a simulation solving those two equations that I show you, the Schrödinger-Poisson equation. They're solving it in a box, in a cubic box, expanding universe. And you can see this interference pattern, right? So the color coding here represent basically density fluctuations. The lighter color is basically higher density. The darker color is lower density. And you can see this is a galaxy halo that eventually form a galaxy, let's say. And this is another galaxy halo. Connecting them is a filament, but you can see interference pattern along the filament. You can see interference fringes around the galaxy halo. And if you zoom into the galaxy halo, you will see interference pattern. And it's really an inevitable implication of having wave dark matter. Okay, so if you have a halo, and the halo can be decomposed into a set of waves, and these waves in general have rather random phases, because when a galaxy halo forms and virialize, it's a fairly messy, violent process. These waves inside a halo, they're random phase, and therefore you are going to have, just by random chance, constructive and destructive interference. It's inevitable. And the scale of this interference pattern is very predictable. It is determined by the de Broglie scale. Therefore, if you give me a galaxy halo, and you tell me, here is the velocity dispersion of the halo, I can tell you what is the typical size of this interference pattern. What's the typical size of a constructive interference patch or a destructive interference patch? And the typical size is the de Broglie wavelength, 1/mb, okay? And there are many, many astrophysical implications of this. I don't have time to go through all of them. Let me tell you about some of the kind of more striking implications, right? I'll be happy to talk about any of these if at the end, if you are interested. But let me tell you about vortices. Turns out to be a very interesting prediction. of wave dark matter. What do I mean by vortices? Vortices in this language are places where, let me see if I should just keep this slide. Hang on 1 second. Okay, so here's what I want to say. Let's forget about the first 2 bullet points. Let me go to the third bullet point. So I told you about interference pattern, right? So if I look at these again, looking at these pictures, there are going to be places where you have destructive interference. Let's imagine for a moment that there are places where the destructive interference is complete. Meaning what? Meaning the destructive interference causes the wave function to actually vanish at a certain point, okay? Indulge me for a second that these places occur. Imagine that happens. When that happens, now let's think about the wave function. When the wave function vanishes, the amplitude vanishes. And if you ask what is the phase of the wave function, the phase does not really make sense if the wave function actually vanishes. When the amplitude is 0, the phase by itself is not a well-defined concept. However, away from this particular place where the wave interference is complete, the destructive wave interference is complete, where the density is not 0, the amplitude is not 0, the phase is very well defined. And what I want to argue is that if you think about how the phase go around, as you go around this place of destructive interference, you will have interesting winding of the phase. Okay, so this is the argument I want to give you. So in 3 spatial dimensions, if you ask me what are the set of points where both the real and the imaginary parts of the wave function vanish, it should generically form a line. And the reason is actually very simple. If in 3 dimensions, if I ask you, I have a function and this is a function of 3 coordinates, and I'm interested in the set of points where this function takes a certain value. In particular, in this case, we're interested in the value 0, right? If you ask me what are these set of points where that function would take a certain value, it has to form some kind of 2-dimensional plane, basically. It's a planar structure in 3 dimensions. I can make the same statement about the real part of the wave function and the imaginary part of the wave function because I'm demanding both vanish. So both of them form some kind of a plane, and where they intersect is where both real and imaginary part vanish. And the place where 2 planes intersect is basically a line. And so generically, always the set of points where you have complete destructive interference has to form some kind of a line. And here I illustrate that with this purple line. As I said before, along this line, the phase of the wave function does not make sense. However, away from the line, the phase totally makes sense. The wave function is not 0. And for the wave function to be single valued, the phase must wrap around by integers of 2 pi. This is what I mean by a vortex. In fact, you can make this precise. I told you under the fluid interpretation, the velocity of the fluid is precisely the gradient of the phase divided by m. And so if you take the fluid and you take the velocity and integrate around a loop, any loop, integrate this around this line, you would get basically integer winding. This is, in fluid mechanics, we would really call this a vortex. This is really very, very much like a vortex that you might be familiar with for superfluid, for example. Not only that, if you follow some simple arguments, you can actually even make prediction about the density profile around the vortex. And the argument is actually very simple. It's just a Taylor expansion argument. Suppose I take the wave function, I expand around one of these points along this line. Let me call that point 0. Taylor expansion tells you that the first order term is 0. The 0 order term is 0 because that is where the wave function vanishes. And then to first order, you have this linear term in x. And that basically tells you close to a vortex, the wave function should be linear in separation from the vortex. which means the density, which is square of the wave function, has to go slightly out square. Okay, so that is a very general prediction. Moreover, the these vortex lines, they cannot just randomly end. It's like a magnetic field. Somehow it has to close in a loop. And so, in fact, this vortex line, they should form a vortex ring, basically. That's the general prediction. For those of you, again, familiar with QCD axions, I want to emphasize this is not the axion string. This somehow resembles the axion string, but this is not the axion string. For the QCD axion, the axion string, the U1 going around is the Petri-Queen U1. Here, the U1 going around is just the U1 associated with the phase of the wave function, which is nothing other than the U1 that enforces particle number conservation because you are in the non-relativistic regime. So this is not the Petri-Queen U1. But this is a generic prediction. And in fact, you can ask, how often does this happen to have complete destructive interference? It's actually more often than you think you might naively expect. It turns out you can show generically you should expect one vortex ring per the Broadly volume. In each of the Broadly volume, you should expect one of these defects, basically. Okay, it's a fairly generic prediction. And you can look for these in simulations. This is a simulated halo. I'm not showing you the halo, but I'm showing you the vortex rings that you can find in the simulation. If you have a nice spherically symmetric halo, it will look like this. If you have a more messy halo, more realistic, the vortex rings would look more deformed. They are there. You can check the density profile that goes like R square, as I said. I think I'm going to skip these comments because I can see I have about maybe 10 minutes left. So I do want to tell you a little bit about experimental implication. So I'm going to skip ahead. I apologize. I don't want to end the talk without going over this slide. So in this slide, I want to discuss what this means, this wave nature of dark matter. What does it mean for experimentalists who try to detect axions in the lab, right? For the axion, the most common, the most common ways to detect the axion is through basically its interaction with the photon. And in the Lagrangian, it looks like this, right? This axion is here. The little f is the axion decay constant. Here, the big F is the field strength. So the axion being a pseudoscalar, it couples to FF dual or E dot B. The generic coupling is like this. So that's one coupling that's often used in detection of axion. For example, ADMX experiment, a microwave cavity experiment, involves basically a cavity in the presence of a magnetic field, a strong magnetic field. The strong magnetic field, which is one of these F, together with the oscillation of the axion, is capable of producing photons, which is this other F, and that photon you can hope to detect, all right? So that's what this little Feynman diagram is supposed to represent. Another fairly well-motivated interaction is the interaction of the axion with fermion, and it looks like this. It's a coupling of the axion with basically the fermion bilinear side. This fermion can be electrons, can be nucleons. And a common way to look for this is to basically observe that if we live in a halo with axions, and because of the motion of the Earth going through the Milky Way and going around the sun, we should expect an axion wind, actually. That picks out a direction, which is some kind of gradient of the axion field. And around that direction, a fermion that is coupled in this way should experience a precession, meaning the axion gradient acts as some kind of magnetic field, basically causes a fermion to precess. And indeed, there are existing experiments that try to exploit this effect, to look for this effect. So there are different kind of experiments. Look for the presence of axions through these two kinds of couplings. And they span a fairly large range in mass. But typically, the mass is not the ultralight mass that I talked about earlier. Typically, the mass is still light, it's still wave dark matter, but not ultralight. Okay. The one thought I want to leave you with is this. Traditionally, experiments that aim to detect axions, what people have in mind is an axion field that acts like this. Suppose I am at a given location where the detector is. The axion field, it would just oscillate in time like this. This is the axion in the y-axis. This is time. The axion just oscillate, right? And people think of this axion as an oscillating field with basically constant amplitude because it's oscillating around m squared phi squared potential. So this seems like a very natural expectation. What I want to emphasize is that because of wave interference, remember the picture I showed you earlier, you cannot avoid having constructive and destructive interference, meaning there's going to be density fluctuations. Which means, for example, in the language of what I showed you earlier, the axion field has this oscillation e to the IMT, which is basically this oscillation shown here. The amplitude is the wave function, and that wave function has fluctuations. It has slower time dependence than m, and so it would cause basically the envelope of these oscillations to fluctuate. So the picture you should have in mind would be something like this. This would be a place where you have basically destructive interference. The amplitude of the oscillation become very small. This would be a place you have constructive interference where the oscillation amplitude is big. And so experimentalists should expect to see this signal rather than this signal. And to give you a sense of scale, right? The oscillation time scale is 1 over m, so that's 10 to the minus 9 seconds if you have 10 to the minus 6 electron volts, okay? The scale, this time scale, going from destructive to constructive interference, I call the coherent time scale. That goes like 1 over mv squared. Notice this powers of v here. This is nothing other than the de Broglie waving divided by 1 more power of v, okay? And this scale, if you put in numbers for 10 to the minus 6 electron volt, is 10 to the minus 3 seconds. This time scale is accessible to experiments. Axion experiments, they integrate on a time scale certainly longer than this. They are looking for oscillations on this scale. This scale is definitely relevant in interpreting the results of experiments. And there are actually some very interesting questions about how we should account for this, how to take advantage of this, and I'm happy to discuss further. I'm just going to leave you with this thought, and I'm going to end because my time is up. So the main few points I want to get across is this. First, if that matter particle is lighter than about 30 electron volts, what you have is more helpfully described as a set of waves, which means there are going to be wave phenomena. And in particular, there will be wave interference. And the kind of substructure that you see in this kind of picture is inevitable, in particular, including vortices. That's point number one. And point number two, this substructure actually has implications for direct detection, axion detection experiments. And I'm going to stop here. Thank you.
Thanks for the nice talk. Very interesting topic. So if we have some question from the audience, please raise your hand or just ask.
So can I ask a question?
Please.
Sure.
Okay. Thank you. Thank you for such a nice talk. So I'm just curious about the effect of black hole here and super radiance in web dark matter case.
Okay, very nice. Black
And
hole
that,
hair.
yeah.
Okay, so let me. It's actually a big subject, but let me show you at least a fun. Let me step my hand. In fact, here's what I'm going to do, because I don't think I'm not. Just bear with me for a second, huh? I think this will allow me to search more quickly. Let me play this movie, and then you can watch this movie and I'll explain what's going on in this movie.
Okay.
So here we are basically representing and actually solving the Klein-Gordon equation in the presence of a black hole, right? So you have a Schwarzschild metric as the background. You have the axion field, the wave diameter field, basically oscillating far away. So the far left is the black hole. Think of the black hole horizon as basically as negative infinity. The x-axis is what's called the tortoise coordinate. So our star goes to negative infinity at the horizon. And far right is where you are basically out there in the halo of the surrounding. You have this axion field that's oscillating. And the oscillation basically send waves falling into the black hole. This is basically what you're seeing. And as the waves propagate towards the black hole, they get amplified and actually increase in amplitude. And you can think of this as some sort of scalar hair for black hole, although probably that is making it overly obscure. Really, this is just accretion, no? This is just accretion of dark matter onto black hole. And but the way the accretion works is a bit different from the way a particle dark matter works, precisely because of the wave nature of the dark matter. And to properly actually predict what's going on, what one needs to do is actually to solve the Klein-Gordon equation in the Schwarzschild background.
Okay. And then this okay, so this, then once the web dark matter is surrounded over around the black hole, then super radiance effect can be happen.
Super radiance is actually is related, but not the same effect. Super radiance actually is a very interesting effect. You solve the same equation, right? Imagine you solve the wave equation. Can you actually see the equation in my slide? This equation, the Klein-Gordon equation is Schwarzschild background. So to see super radiance, you solve exactly the same equation, but you impose a different boundary condition, right? In the movie that I show you, the boundary condition is the scalar field approach some basically asymptotic value, some constant amplitude oscillating in time. In super radiance, you do something different. You assume the scalar field actually vanishes. It actually goes to zero, far away from the black hole. And you assume the scalar field is again ingoing into the horizon, at the horizon of the black hole. If you impose those two boundary conditions, it turns out you can show, and here you want to do actually turns out not a Schwarzschild black hole, but a curved black hole. It turns out if you have a rotating black hole, there is an instability, and that instability is super radiance. So you will find solutions that actually grow with time, and that is the phenomenon of super radiance, which is a very interesting effect. It basically tells you if you have a curved black hole, and if you have a scalar field of the right mass meaning if the mass has a Compton wavelength that's roughly equal to the horizon size of the black hole, then that scalar field actually is unstable, meaning even if you have like one particle around the curved black hole, over time, you would grow more and more particles. That's called the super radiance instability. And you might ask, where do these extra particles come from? You can really interpret them as coming from the black hole itself. You are basically extracting energy and angular momentum out of a curved black hole. That's what superradiance is. So it's actually a different phenomenon from this accretion in this movie that I show you. Does that make sense?
Yeah. And then this web nature of dark matter will be reflected in the super radiance in certain way, if we assume the interference and or the this interference pattern. No,
can you say question again?
So I mean that if we assume that this particle is like web nature of the particle, what we are assuming web dark matter, let us say,
Yes.
then
yes.
Once the super radiance happens, then it creates a large number of particles, right? And then
Yes.
we may expect some interference pattern of it, as the nature of this web dark matter. Can it be reflected in the spectrum?
Very good, very good. So if you actually work out the instability of the of, let's say, an axion with the right mass around a curved black hole, the instability actually depends on the energy level of the particles, in particular on the L and M, the angular momentum numbers for the particle. And generally, in fact, the energy level works rather like a hydrogen atom. It's really like having a hydrogen atom with its levels. And it turns out, generally, the instability rate is the highest for one particular level. And so in this superradiance situation, the general expectation is, yes, in principle, you can have interference between different levels, but the general expectation is because one level grow much faster than the others, you'll be dominated by just one single level usually.
Okay.
And so you don't have interference between different levels too much. But at some level is there. At some level is there, but mostly you are dominated by the one that grows the fastest, basically.
Right. Makes sense. Yeah. Thank you very much. Yeah.
Thanks for asking. I'm
So
going to stop.
I have a question.
Please.
So we have wave dark matter, which is let's say we can consider it as a classical phenomena. And
yes.
On the other hand, for these very light particles, we can form Bose-Einstein condensates, which is a quantum phenomena, which is a quantum phenomena. So how will you connect both things?
Yeah, very good. So it's a question that get often asked. Let me say the following. For the most part, let's look at pictures now. Let's look at this picture again. For the most part, when you see pictures like this, wave interference, these waves really should be interpreted as classical waves, as I emphasized before, just like we interpret electromagnetic waves, classical electromagnetic waves that describe a stage with many photons. These waves should be interpreted in a similar way. There is a phenomenon of Bose-Einstein condensation, and it tends to happen in the following way. It tends to happen in the centers of halos. Let me see if I can find a picture. You see this picture? This is a picture of what kind of a generic dark matter halo would look like. You see lots of fluctuations. The lighter color, the higher density, the darker color is the lower density. These are the constructive and destructive interference pattern I was talking about. The size of each of these granules is about the Rayleigh wavelength. The Bose-Einstein condensation occurs where? It turns out to occur basically in the middle here. There, basically, the axion field or the wave dark matter field, it tends to collect and condense into a ground state. Now, this phenomenon is basically a combination of the fact that you have waves and you have gravitational interaction. The two is sufficient to cause this phenomenon. I would not call this I would not call this a quantum phenomenon for the following reason. If we ask, how is this halo generated? Well, this halo is generated by basically solving the same equations that I was telling you, We were solving the Schrödinger equation and the Poisson equation, where this psi is really just a classical field, and the gravitational interaction is enough to cause basically a collection of particles going into the ground state in the middle of halo. I think I'll just leave it at that.
But how you can produce inside, I mean, the core, you can produce the, I guess if we have a Bose-Einstein condensate, we have a Bose-Einstein distribution, right? And not Maxwellian will be the classical case, I guess. How you...
Yeah, it's not Maxwellian. If you actually ask what is the distribution function, for example, there is a concentration, high occupation in the ground state, just what you expect for Bose-Einstein condensation. Now, if you ask why does this happen, the reason why it happens is because is basically because of a phenomenon we call gravitational cooling. Let me try to give you an analogy. Something like this happened even not for waves. So imagine, and we know this happens for globular clusters. So globular cluster is basically a system with about millions of stars. And a very old globular cluster tends to have a density spike in the middle, at the center. And we understand very well why that happens, because essentially the stars, they scatter, they gravitationally scatter each other. And occasionally what happens is some of the stars that are very close together, they form binaries, and they would encounter a third star, kick that star out of the globular cluster, and that binary becomes tighter, become more strongly bound. And these more strongly bound stars, they collect at the center and causes a density spike. The phenomenon that we are seeing here is basically the wave version of the same thing. It's basically the gravitational interaction between these interference granules. They gravitationally scatter each other. Remember, these granules have the Broglie size. This is kind of the coherent size. They gravitationally scatter each other, and then they collect at the center, basically forming this ground state. That's the way we understand how this happens. We can see this in simulations. It's fairly, it's repeatable. People have done this at many different resolutions and checked this. It seems to be very robust.
So only by using classical equation of motion, you can get that state?
Only by using classical equation of motion.
Okay.
And it seems to happen only at the center of these halos, as far as we know. There are some remaining questions to what extent that happens actually elsewhere. To our knowledge, so far people have not seen that. It only happened at the center, rather like the center of globular clusters. Seems like a very similar phenomenon. Yeah.
Okay. Thank you. Thank you. So we have.
It's a good
yeah.
question.
It's clear. It's clear. It's clear. The answer is clear. I have my doubts, but your answer at least was clear. Thanks. So I'm sorry. We have some questions in the chat.
Hi, Professor.
Stop sharing. Hi.
Last talk. Thanks for your last talk. I have some questions text to the chat room. Can you check that?
Sorry. What was your question?
My question has text to the chat room.
Oh, the chat. Let me
you
see.
Can see the chat. Yeah.
Let me see the chat. Okay. You have mentioned the particle physics motivation. Can you give some comment on the other motivations? Like, can it solve other standard model puzzle as well? Well, in some cases, yes. The most famous example is, of course, the QCD axion. No? The QCD axion, in fact, was originally invented not to solve the dark matter problem. It's invented to solve the strong CP problem, namely why the QCD at the theta angle is so small. Right? So in the QCD Lagrangian, in principle, there should be an operator that goes as basically GG dual, G meaning the gluon, multiplied by some angle is called the theta angle, and somehow that's known to be very small, constrained by the measurement of the neutron dipole moment, which so far there are only upper limits, but the upper limits are so strong that the theta angle must be very, very small. And the QCD axion was a mechanism invented by Pesci and Quinn to actually solve that problem. Essentially, they promoted the QCD, the theta angle into a dynamical field, essentially, and use that to argue why it takes such a small expectation value. So it is an example of what you are asking for, where a particle is motivated by something other than dark matter. It solves some other standard model puzzle, but turns out to be useful in thinking about dark matter as well. Yeah, the QCD axion is probably the most well-known example of that.
I want to know, is there any, some novel idea, another novel idea? The strong CP problem is what I have here before.
You are asking other motivations?
Yeah, other.
Well, other motivations, I would say they are more indirect, no? So for example, the string theory axions. The string theory axions, again, they are not somehow invented to solve dark matter problems. They are somehow an outcome of string theory computations, let's say. And string theory, of course, was motivated by the search for a theory of quantum gravity, right? So that is that's a totally different motivations from the dark matter problem. I don't know whether that's enough to satisfy you, though.
Okay. I have another 2 questions in the chat.
Another 2 questions. Let's see. The amplitude density fluctuations. I want to know if the amplitude density will be affected by other factors. So sorry, I'm not sure I understand the question. The amplitude density fluctuation is around, what is this? 0 to 2p local. I'm not sure. 0.2 rho local.
Rho local.
I'm not sure what is meant by that actually.
I mean, you have mentioned the interference of the wave dark matter. Once there have influence, I think the local density is fluctuation from 0 to 2 times of local density. How this can it be affected by any other factors?
Are you talking about the wave interference substructures?
Yeah.
Yes, good. Yeah, the wave interference substructures, so the generic prediction is something like this. Delta rho over rho is basically order 1. So the amplitude is order 1, which means the rho can go all the way to 0. That's kind of the floor, but the rho can go up to, let's say, a few times rho, and 2 rho would be a fairly typical prediction. But there is really a whole range. The amplitude actually obeys a probability distribution, and the probability distribution actually is exponential.
Sorry, I think he's asking if there is other factors that can make fluctuations on the density, not only the interference.
Not only the interference. Yeah, there are totally other factors. For example, let's look at the Milky Way, right? Look in the Milky Way, besides this wave interference pattern that I was telling you about, which give you order 1 fluctuation in the density, let's say, inside the Milky Way, clearly there are satellite galaxies, no? There are, inside the Milky Way, there are subhalos. Those subhalos is also some kind of substructure. Where do they come from? Well, they just come from smaller halos that over time merge onto the Milky Way. So that density fluctuation is also there. And it's not so much because of random wave interference. It's just the existence of smaller subhalos that merge into Milky Way. So that would be another kind of density fluctuations.
Okay,
Let me look at a third question. Fuzzy dark matter around really differ from. Well, the main difference is actually the ultralight version has very long, the Broadly wavelength is astronomical. If you are not ultralight, the Broadly wavelength is much smaller. And so in terms of astronomical observations, the ultralight version would be much more easily observed. If it's 10 to the minus 6 electron volt, it will be very hard to see the sign of the interference pattern in astrophysical data, except the direct axion detection experiment. If they can detect the axions, let's say ADMX, they will see the interference pattern. That would be a prediction. But through the telescope, through astrophysical methods, normal astrophysical methods, only the ultralight end of the spectrum, you would be able to see, be able to observe the interference pattern. Through, for example, gravitational lensing, through the heating of the stars. There are many different ways, but yeah.
Oh, thank you. I understand that. You mean the gravitational aspect is different from the direct detection aspect, right?
Yeah, exactly. So for the ultralight end of the spectrum, the way to detect to see the interference pattern, you can actually see them fairly. At least it's fairly promising that we can see them astrophysically from lensing or the scattering with stars. If it's not ultralight, if it's like only light, like 10 to the minus 6 electron volt as an example, then it will be very hard to see the effect through gravitational lensing. And the only hope you will be able to see what is going on is actually with direct detection. But with direct detection, it's guaranteed you will see the wave nature in fairly dramatic ways. You will actually see the interference pattern in your direct detection signal.
Okay, thanks. Thank you. Thanks.
So we have maybe time for one more question, and
Yes, can I ask a question?
Yes, please.
Thank you for the talk, Professor. The first question is is about the dynamic equation of the wave dark matter.
Mm-hmm.
It seems that the dark matter will, the dark matter will form the dark matter cloud, and you mentioned in the final part of your talk, you mentioned that there will be some boson condensation in the core of a halo. So I wonder that if the dark matter halo is so massive, is it appropriate to use Newtonian gravity to describe the gravity field around the boson condensation? Will GR give some correction to the dynamic of the, some wave interference effect?
Very good. So the general relativistic correction are typically important if you are close to black holes. You have to be very close to very compact objects. Because, in the Milky Way, for example, even if you go to the center of the Milky Way, the velocity is not that big. It's nowhere near the speed of light. Let me put it in another way, So you can also ask, well, how big is the gravitational potential, right? Gravitational potential again, I'm using units where the speed of light is 1. The gravitational potential in the Milky Way is about 10 to the minus, it's around 10 to the minus 6, which is much smaller than 1. And that basically tells you is actually a fairly good approximation to use Newtonian gravity. The only place inside our galaxy where Newtonian gravity is not a good description is if you get sufficiently close to a black hole, then okay. Or maybe a neutron star. Then okay, you need to start thinking about general relativistic corrections.
Yes. Does you mean even if in the both condensation, the dark matter is not denser enough, that the GR correction is important?
That's right. It's not dense enough. If you want to think about the central soliton, which is usually the name given to this object that is in its ground state, it would become relativistic only under one situation, is when the soliton reaches maximum mass. It turns out there is a maximum mass. And when you reach that maximum mass, it's kind of the analog of Chandrasekhar mass, if you want, for white dwarfs. When you reach that maximum mass, then you'll be close to relativistic. And in fact, when you reach that mass, in fact, the soliton becomes unstable, and in fact, it will collapse, presumably to a black hole. Only then, but the soliton inside the Milky Way is nowhere near that maximum mass.
Okay, thank you, Professor. And can I ask a second question, if the time is okay?
Yeah, please.
It's up to the organizer. Yeah.
You mentioned that the destructive pattern in 3 dimensions is like a ring, but and you use the analog to the to the magnetic field, and I still a little bit confused why the destructive interference pattern must be a ring.
Yeah. Are you asking whether why it has to close, or are you asking whether it has to be one-dimensional?
Why it has to be closed?
Why it has to be closed? Well, suppose it's not closed. So let's assume it's what's closed. What happens at the end point? I guess that's the question.
Yeah. Why?
Yeah.
Why it is not a string that it extends to infinity? So
oh, to infinity. Oh, to infinity. In principle, yes. In principle, it can. In principle, it can. In practice, nothing really literally extends to infinity, so it closes. But in principle, yes. In principle, you can construct solutions where the vortex just extend all the way to infinity. That's a completely fine solution. But it's more like a very idealized solution. In reality, nothing really extends to infinity, so it's more like a ring is the more realistic thing that you will find out there in nature. It's a very similar thing about magnetic field too, no? You can certainly imagine a set of currents that give you a magnetic field that go out all the way to infinity. And so it looks like your magnetic field line never closes. But of course, you know that is a very idealized set of currents that give you that. Realistic currents does not do that. So it's very similar here.
Okay, thank you, Professor.
Okay, so
thanks for that.
Thank you. Thanks again for the nice talk and for answering all the questions. And yeah, so we're done for today, and we would like to ask you if you can share the slides, please, with us.
Yeah, I can send it to you.
Okay, thank you.
Okay, thank you.
So bye everyone. Thanks for coming to this nice seminar, and thank you for the speaker for the nice talk. So,
thank you. Thank
bye.
you. Have a good day. Bye bye.
You too. Bye bye.